Hello everyone, my name is Tianyu Li. I'm a graduate student from University of Maryland, and today I'm going to talk about a very interesting structure transition behavior that we have observed in a type of oxygen storage material. So let's just directly go to the material itself. So the material I'm going to talk about today is a LnMnFeO4 structure material. The structure is shown here. As you can see, it has a hexagonal layered structure, adopts a alternating layered framework. The first layer is the rare earth metal oxide octahedral layer. The second layer is a bilayer system. It's a bipyramid iron oxide layers. So in this bilayer system, half the irons are in the 2+ state, the other half are in the 3+ state. For this type of material, it was found this material can uptake some oxygen into its lattice, and then all the iron 2+ will be oxidized into the iron 3+. At the same time, there will be a structure phase transition happening. Initially, it has R3 bar M structure, and after the oxygen uptake, it becomes the oxygen O4.5, which is a P3 bar structure. Another very interesting behavior on this material is that after the oxygen uptake, there will be some structure modulations happening. Here just choose the electron diffraction images of the material. As you can see in the oxide phase, there are some satellite peaks appearing surrounding the main diffraction dots. That's usually the sign of the structure modulations. The exact material I'm going to focus on today is the manganese substituted variant. So we actually replace the iron 2+ with the manganese 2+. The motivation is simple. We actually take the concentration on the electron configurations. If we look at the electron configurations of the transition metal for the unsubstituted variant, we have the iron 2+ in the reduced state, which is D6 configuration. So during the oxygen uptake, the iron 2+ becomes iron 3+. So the electron configuration transits from D6 to the D5 in the structure. If we replace the iron 2+ with manganese 2+, the manganese initially is a D5 state. So after the oxidation, it becomes manganese 3+. So the transition is from D5 to the D4. So as you can see here, right, if we do the substitution, the electron configuration transition will be totally reversed from the original unsubstituted variant. And we want to check how does that influence the structure behavior of this type of material. So we actually synthesize the substitute variant. We synthesize the ytterbium manganese iron O4, and the first thing we did is to examine whether the substituted material still has the ability to uptake the oxygen. It turns out it does have. Here just choose the TG data. Heating in the oxygen, as you can see, the material can uptake the oxygen into the lattice upon the heating, and based on weight gaining, we find that the chemical formula of the oxidized phase is ytterbium manganese iron 4.5. And we also did the in situ diffraction characterization on the material upon the oxidation and reduction. It does show upon the oxygen uptake, there's a phase transition happening. And if we put the material back to the reduced environment, the phase can actually be recovered back to the original reduced state. So then we focused on the crystal structure of the material before and after the oxygen uptake. So we did both synchrotron and neutron diffraction measurements on the material before and after the oxidation. So for the reduced phase, we did review refinement on the diffraction pattern. For the oxidized phase, we actually have to use charge flipping to partially solve the structure, and then using the difference free map from the neutron diffraction to locate the positions of the sums and oxygen. And here just use the fit. As you can see, there are still some tiny peaks cannot be fitted by the average structure, which is actually the satellite peaks coming from the modulation, which I will talk about them later. So now we have the average structure, so we can try to look at how does this transition happening, right? It turns out to be when the original phase uptakes the oxygen atoms are inserted in between the iron oxide double layers here, and it seems there's a very huge repulsion force, so layers will undergo a shift in both A directions and B directions that kind of leads to the structure transition to the new phase. So even though if you just simply look at the symmetry, right, they have totally different space groups. However, this two structure, right, is highly correlated, and that kind of explain why this transition is highly reversible. Here, when we look at how does this oxygen uptake influence the local structure of the material. So the first thing we did is to use the Raman spectra to characterize the material. Here shows the spectra for the material before and after the oxygen uptake. The more major difference that we have observed lies on this A1G peak. We actually see, right, after the oxygen uptake, this A1G peak blue shift to the high wave number. The A1G peak in the original phase corresponds to the stretching vibrations along the C directions. So the shift actually indicates the oxygen uptake can lead to either a stronger bonding covalency or a shorter bond distance along the vertical directions. This actually was verified by the pair distribution function analysis from the neutron scattering. We found that for most of the atomic distance on the vertical directions, those distances are shortened after the oxygen uptake, while for the distance along the horizontal directions, most of the distance are shortened after the oxidation. And then the modulations. Here just choose the high resolution TEM image and the electron diffraction patterns of the grains before and after the oxygen uptake. As you can see, even just simply look at the high resolution TEM images, you can already observe the structure modulations, right? There's some aperiodic structure which is larger than the atomic scale here. And if we look at the electron diffraction patterns, right, you can actually see there's a very pretty and highly symmetric modulation or satellite peaks appearing in the diffraction pattern. That's a sign of the modulation. Of course, we did observe those satellite peaks in the powder diffraction patterns, no matter for neutron or synchrotron X-ray diffraction. We look in detail on those satellite peaks, we actually find that this modulation is a two-dimensional modulation, as we couldn't find any C direction components in the modulations here. And also, you can see there are actually 12 modulation vectors surrounding, and same these 12 are identical to each other, right? And based on the arrangement of the modulations here, we can kind of extract some of the symmetry elements that exist in the modulation vector. So one is we find that it seems this threefold rotation axis still applies for the modulation vector, and that still invariant center remains because it seems it actually can, right, it lies here. And of course, we find that the Gleim plane symmetries can still be applied on the modulation vector. So it's still highly symmetric. And in the middle, it just shows the image when we put the modulation vectors on the rhombohedral cell. And as you can see, these 12 modulation vectors are actually the same, right? Identical to each other. And the direction of the modulation vector actually aligns exactly on the diagonal line of the two-unit cell. So we also tried to measure the modulation vectors on the electron diffraction patterns, and we indexed the modulation vector on both neutron diffraction and the synchrotron X-ray diffractions. The value of the modulation vector we get are actually very similar to each other from different measurements. And the value are actually very close to the integer 1/7, 2/7, and 0. Then we refine the modulation curves for each of the atoms in the structure with the superspace group approach, and we find the most obvious or strongest modulation happens on the O2 and the O3 atoms. Of course, for this part, I can spend a lot of time elaborating the modulation curves, but I don't have time, so I will just give you the conclusions that we draw from the analysis. So it turns out in the modulated structure, in the average structure, since there's an invariant symmetry there, the O2 atom can actually well, there will be two O2 atoms within one unit cell. However, because of modulation, the O2 can only appear once, either on the right or on the left in the unit cell. So it's roughly a 50% occupancy. And same for the O3 atom. It turns out O3 can occupy two very close sites. However, they cannot appear at the same time. They actually occupy that alternately in different unit cells. And we actually find there's a coexistence of the bipyramid and archedral oxide within this iron or manganese oxide bilayer systems. So that's pretty much about the structures. We also try to explore how does the oxygen uptake influence the magnetic properties of this material. So we did AC susceptibility measurements and the neutron diffractions at different temperatures. So the AC susceptibility measurement shows this material is actually a spin glass, and it has a glass transition temperature around 60 Kelvin. However, if you look at the neutron diffractions, we find that well beyond this transition temperature, there's already a short-range magnetic ordering appearing. If you look at the detail on the magnetic peaks, we find there's a Warren line shape here. So very clearly, this ordering is a short-range two-dimensional magnetic ordering. Here is just a qualitative analysis on the super-exchange interactions, which I will skip. Let's go back to the oxidized phase. It turns out for the oxidized phase, it's still a spin glass. However, the glass transition temperature is greatly reduced to 30 Kelvin from the 60 Kelvin upon the oxygen uptake. And also, it turns out there are two transition temperatures, one at 630, another at 10, which I actually have no clue on that. I still need to figure out what is happening here. Anyway, if we look at the neutron diffractions, what we have observed is that the short-range two-dimensional magnetic ordering are greatly suppressed after the oxygen uptake. As you can see, the peak actually disappears, right? And of course, we also did the same measurement, exactly the same measurement on the lutetium case and the yttrium case. What we find are very similar results. As you can see here, just shows the result part of the results of the lutetium samples. There are still structural modulations upon the oxidation, and the magnetic behavior are also very similar to the ytterbium case. That's pretty much more about today for my presentation. And here's just a conclusion. I hope my presentation persuaded you on this type of material are very attractive and has very interesting structure transition behaviors. And in the end, the acknowledgement. In this project, I really got lots of help from the previous student in our group, especially from Dan Taylor and Dr. Rishvi Javerslik. I also appreciate the help from Dr. Liu, who helped me a lot in TM image taking. And finally, this project is funded by the NIST award. That's it. Thank you.